This is part two of the resonance videos. For this video, we're going to be focusing on some common mistakes and how to avoid them, and then looking at some advanced problems related to resonance. So for this first common mistake, and this is probably the most common mistake I see, is people accidentally making 5 bonds to a carbon. So a carbon can maximum have 4 to not go over its octet. However, when we get into more complex structures, such as this one over here, we know that this lone pair and the double bond can participate in resonance. And so if we were to start drawing our first structure, we could bump down those lone pair of the nitrogen down to this bond. However, if we stop the structure here, the problem that we encounter is that this carbon right here, this purple one, now has 5 bonds if we include that hydrogen that's on the structure. And so we cannot stop this structure right here. This is not a valid resonance structure. And so to account for this, what we want to do is we want to move that other double bond one more step over. And so if we were to start off with the same structure here, I'm just going to copy it over here. What we can additionally do is add in the second arrow to move this double bond up to this carbon right here. And so our structure with this ends up being looking something like this, where we have a positive charge on that nitrogen, and then that lone pair is now on that carbon over here. And so this is okay. The other type of error that I see related to this type of molecule that also involves 4 potential bonds, or going over the 4 potential bonds, is something like this. Where we also start off with the same structure. I'm just going to copy it over again. However, in this structure, instead of moving up the electrons to the next door carbon, what some people might accidentally do is move over those electrons 1 bond instead. So instead of going from the double bond to an atom, they're going from double bond to double bond. And so if we were to draw out this structure, or the product of these arrows, we would get this. And so that carbon that we initially had a problem with in the beginning is fine. So this purple hydrogen that I just drew in, that one is completely fine. We have 4 bonds on this carbon. We're good here. However, the problem with this structure is that if we take a look at this bottom carbon right here, we actually have 2 hydrogens here. And so now we unintentionally made 5 bonds to this bottom carbon right here. And so we can't have 5 bonds, and so this is also not a relevant structure here. And so whenever we're moving electrons around, we have to make sure that we're not accidentally creating 4 bonds, especially to a carbon, because a lot of times those hydrogens are omitted in the initial structure. And so you have to make sure that you're not accidentally making 5 bonds. And to avoid this, my biggest recommendation is to draw in all the hydrogens immediately. So draw in all hydrogens and keep track of them throughout the resonance structures. And then the other tip, and this is repeating something that I mentioned in my previous video, is avoid all sp3 hybridized carbons. Or in other words, any carbon that has 4 single bonds. And so, for example, for this example here, on this last one, this bottom carbon initially was an sp3 hybridized carbon. So knowing that, we should have just not drawn anything to it. We should just avoid this one right here. I'll just write sp3 here. All right. The next common mistake, and this also goes for any sort of reaction mechanisms in which you're using arrow pushing, is accidentally swapping the direction of arrows. That could look something like this, where let's say you're starting off with this structure here, and you want to illustrate the resonance structure where that double bond shifts over. A common mistake that I see is people accidentally starting with this carbocation and going towards the electron pair. And so we always have to make sure our arrows start at the electron pair, not where they end up. So never, ever, ever start a lone or an arrow from a positive charge. And always start with the electron pair. And I think something that helps people keep track of electrons when they're first starting off with resonance structures is just making like using color coding to show where electrons ended up. So for example, we could highlight this electron pair right here in green and show that it ended up right here. And so we're kind of keeping track of it in this way. And so here I'm just going to also write that arrows should always start at the initial location of the electron pair. And then go to where they end up. All right. So for moving on to this next common mistake, which is jumping an extra bond. Sometimes when we are given a structure that looks like this, we get something that kind of looks like it could potentially engage in resonance. We have a double bond and then a positive charge that's over here. However, what we can see here is that we're separated by an sp3 hybridized carbon. This carbon has two hydrogens right here that aren't drawn in the skeletal structure, but we should know that they are there. And so we can see that that carbon already has 4 single bonds, and so it cannot participate in resonance. And so similar to what we talked about under common mistake number 1, we need to avoid this carbon at all costs. We never shift electrons through it. And so for this one, we can't jump 2 carbons to avoid it to draw out this structure. This would not be a valid structure here because we jumped more than 1 bond to end up with that arrangement here. And so this initial structure doesn't actually have any resonance that can distribute that positive charge throughout the molecule. We're kind of stuck with where it is in the structure. I'm just gonna make a note here that double bond electrons always go next door. We never go further than 1 carbon away. All right, so these are probably the most 3 most common mistakes I see. I think honestly getting used to resonance structures is all about practice. And so I really recommend taking a look at the practice problems worksheets that I posted for resonance structures. The beginning of that worksheet is really about getting comfortable with arrow pushing. And then at the end, there's some drawings for resonance structures that might be useful to compare your own understanding to. These next sets are going to be a little bit more advanced. They're going to focus on what can you gain out of resonance structures or what information you can get from resonance. And so for this first one, we're going to take a look at how do we use resonance structures to identify which regions of a molecule are electron deficient and which are electron poor. And so a lot of questions in organic chemistry can be answered in relationships to resonance. So it's something that you'll have to do throughout the entire year. So the sooner you are most comfortable, or the soonest you're comfortable with thinking about a problem through the lens of resonance, the easier the course will be. And so let's take a look here. As I've said before, anytime that we see a carbonyl, the first thing that we should be thinking of is this resonance structure, where we move the electron pair in the double bond up to the oxygen. And so here I will draw out the structure. So now we have 3 lone pairs on the oxygen. And this lone pair is the one that was initially there. And now that carbon at the bottom has a positive charge because it doesn't have a hydrogen, because in the initial structure, it already had 4 bonds. So in this structure on the left, we do not have a hydrogen. And so there shouldn't be an extra one in the new structure. All right, from here, we can draw out that next resonance structure that we can get from shifting over this double bond 1 spot over. And so now what we get is that this terminal carbon now has that positive charge. And recall from my previous video, we always want to make sure that the net charges end up being the same across all the structures. So here we don't have any charges, so we're at a charge 0. In this middle one, we have a +1 and a -1, so we're also at a 0. And then we'll talk about how we get this charge in a second, but in this one, we also have +0, so we're good with the charges across these resonance structures. But let's talk about how I got that +1 for that left carbon, for this carbon right here. So the first thing is to first check how many hydrogens we have on that carbon. So if we go back to our initial structure here on the left, we can add in those 2 hydrogens that we know that terminal carbon has to have. And so since resonance structures don't change in the number of atoms that we have, this one should have a hydrogen, also have 2 hydrogens here on the end. And so what that means is that this terminal carbon right here only has 3 single bonds and no lone pairs. And so it has an overall plus charge. And whenever you're drawing a resonance structure, as I've said in the previous video, always make sure to stop and double check that you have all the charges that you included. All right, so from here, what we can do is use these to draw out the resonance hybrid. And so for that, we'll do exactly what we've been doing, where we draw out the single bond skeleton structure, and then we'll add in that double or that dashed line to represent the location of the double bonds across the structures. And then we'll add in our deltas corresponding to where we saw charges in the initial structure. So here we had negative charges on the oxygen, so we'll have a delta minus right here. We had a positive charge on this terminal carbon, so we can add that in here, or a delta positive. And then the last one is we had a positive charge on this carbon in the middle, so we also have a delta positive there. And so now we have our resonance hybrid. And so from here, we can identify the electron rich and the electron poor sites. So wherever we see a delta minus, that means that this is going to be electron rich. And so that means that that oxygen within the hybrid state of its electron distribution has some extra electron density on that oxygen relative to what a neutral oxygen should have. Then any place where you have a delta positive is going to be electron poor. So since we have that partial positive charge, we know that that location is deficient in electrons and potentially wants to gain electrons. And then this terminal one right here is also delta positive, and so this terminal carbon is also going to be electron poor or electron deficient. And so this is the reason this is important is because as we get into reactivity within organic chemistry, we're going to see that a lot of the types of reactions that happen are due to these partial positive or partial negative sites on the molecule. All right, let's do this next one. So this one is, which of the following charges is more stable? and then use resonance structures to justify your answer. And so we can take a look at the differences in the structures here. And so what we can see is that this left one can engage in resonance. This double bond is close enough to this positive charge where we could draw this structure here. Where that that positive charge ends up being on that top carbon. We could similarly draw one more where we end up shifting this double bond over. And again, that's because that double bond is only one carbon away from that that positive charge. And so it's close enough to shift over. So we end up with that final structure. And so what we can see is that the positive charge here is kind of distributed across the molecule. So what we end up having is that instead of having a concentrated positive charge in one location, the actual charge ends up being something like effectively being a third of a positive charge because it's spread out across those three locations. And then later on, we're also going to talk about how to compare these different positive charges and which one would be more or less stable. But for now, what we should know is that whenever you have resonance and spreading out of a charge, that charge ends up being more stable. Then if we take a look at the structure on the right, what we can see is that this double bond is too far away from that positive charge to engage in resonance. And so as a result of that, we do not get any stabilization of that positive charge. And so that charge ends up being a lot more reactive, or not the charge itself, but the location on the carbon ends up being much more reactive because there is no stabilization. And so to answer our question, we see that the resonance stabilized positive charge is more stable. And so altogether, the structure on the left is going to be more stable. All right, this last one is just focusing on some extra practice problems related to some more complex molecules. So here, similar to what we did in that previous question, we can see that we have this carbonyl. And then we also have a nitrogen right here that has a lone pair of electrons. And so what we'll see is that both of the nitrogen is capable of engaging in resonance with that carbonyl. So let's start off with filling in all the lone pairs. And then in our first step, as we've talked about, the very first thing we want to do is bump up those electron pairs from the double bond to the oxygen. And so we'll end up similar to what we did above, we'll end up with this structure here where we have 3 lone pairs on the oxygen. And so in the previous one, we next had a double bond shift over. However, here what we have is this nitrogen lone pair that is capable of jumping down and forming a double bond. And so we end up with this structure here. And so here we also want to pause and just double check that our charges are okay. So here we have +0. Here we also have +0 because this positive and the negative cancel out. And then here we're missing a charge because right now we only have this negative charge. And so we want to double check our structure to make sure that we have that or include that positive charge in the molecule. And so we know that this carbon right here is now satisfied because it has the 4 single bonds, or 4 total bonds, I should say. It has 1 double bond and 2 single bonds. However, this nitrogen right here
now has a total of 4 bonds and 0 lone pairs. And so because it only has those 4 bonds and doesn't have a lone pair, it has a positive charge because we know that nitrogen wants to have one single lone pair in its neutral state. All right, so that's that group here. All right, let's move on to this next one. So here we can see that we have a positive charge and then some double bonds. And so here, what I highlighted is all the atoms that can participate in the resonance. We know that these 2 carbons that are left over here on the left cannot participate in resonance. So we do not touch them. And again, that's because they already have those 4 single bonds each, so they cannot participate. But all the atoms involved in this green part can. And so we know that whenever we have a positive charge, what we should be thinking about is how do we get electron density over to that positive charge? So we don't want to start our arrows at the oxygen. We want to think about where can electrons shift over to provide that oxygen with electrons. And so here what we can see is that there's a double bond that's directly adjacent to it. And so we can use that double bond to shift the electrons up to the oxygen. And so now that oxygen ends up with 2 lone pairs. However, what we have to double check is our charges again. So if we were to draw in the hydrogens on this carbon that's right below the oxygen, we know that in the initial structure, to fulfill this octet over here, we have to add in 1 hydrogen. And so here we only have 1 hydrogen, which means that that carbon over there only has 3 bonds. So we can add in that positive charge to that carbon. And then in the next one, the next step, we can also do something similar to what we did in one of the previous questions, where we shift over that double bond to that positive charge. And we end up with this here. And so now that a carbon that had the 3 bonds now has 4, so there's no more charge over there. However, this carbon on the left is now the one that only has 1 or 3 bonds. And so it will have a positive charge here. All right, so I think that wraps up this video. Again, I really recommend doing those practice problems that I wrote out and then watching the video for how to solve those.